In this video, we will be talking about how the components of stress are transformed under a rotation of coordinate axis. Our discussion of transformation of stress will deal mainly with the plane stress, which is a condition in which stress vector is 0 across a particular plane. And in our case, the stress components associated with z plane are all 0. Let's consider a plane stress element that is defined by stress components sigma x, sigma y and tau xy. Now, what we want to see is what happens to these stresses when this element is rotated by certain angle theta. The x and y are the original axis, while the x prime, y prime is the new set of rotated axis. Since the stresses change with the orientation of the element, the new stress components are sigma x prime, sigma y prime and tau x prime y prime. The expressions for these new stress components are: the expression for normal stress sigma y prime is obtained by replacing theta in equation 1 by angle theta plus 90 degree. Since cos to theta plus 180 degree equals to minus cos to theta and sin to theta plus 180 degree equals to minus sin to theta, we have the final expression for normal stress along y prime axis as. Now, let's see what this expression means graphically. We can see that the graph ranges from 0 to pi along theta axis. This is because the stress orientation of element resembles its original form at 180 degrees of rotation. So, rotating the element again from 180 to 360 is same as the rotation from 0 to 180 degrees. This makes graph repeat itself at every pi interval. The graph for sigma x prime shows that the normal stress is maximum at a specific angle theta p. Likewise, the minimum normal stress is 90 degrees far from the maximum normal stress. These maximum and minimum normal stresses are called principal stresses, and the angle theta p is called principal angle. Now, if we overlay the curve of shear stress in this graph, we can see that at the points where the normal stresses are maximum and minimum, the shear stresses are zeros, and the maximum shear stress is at angle 45 degrees far from the principal stresses. We saw how sigma x prime and sigma y prime are 90 degrees apart while writing their expressions. Now we will see what that means in a graph. One way to look at this is, if we take a portion of sigma x prime located to the right of point pi by 2 and shift it towards the left by the same amount, we can see that the shifted portion fits the curve of sigma y prime perfectly. And the other way to look at this is, since sigma x prime and sigma y prime are 90 degrees apart and principal stresses are also 90 degrees apart, at point where the sigma x prime is maximum, the value of sigma y prime is minimum and vice versa. Before drawing Mohr circle, let's see what the sign conventions are. When the shearing stress exerted on a given face tends to rotate the element clockwise, the point on Mohr circle corresponding to that face is located above the sigma axis. Likewise, when the shearing stress on a given face tends to rotate the element counterclockwise, the point corresponding to that face is located below the sigma axis. For normal stresses, the tensile stress is considered as positive and is plotted to the right, while the compressive stress is considered as negative and is plotted to the left. Let's draw Mohr circle and let the steps speak for themselves. We should know that the angle in Mohr circle is twice the angle defined by real orientation of a stress element. This is why two principal stresses are 180 degrees apart and maximum shear stress is 90 degrees from principal stresses. Therefore, to bring the stress element to the principal stress configuration, we need to rotate the element by angle theta p, while the line Cx in Mohr circle has to be rotated by angle 2 times of theta p. We notice that the sense of rotation is same for both, that is, both are anticlockwise rotations. Let's see that animation again and end the video.